share the screen. Okay. Okay. So for this week, let's start with probabilistic modeling with discrete systems, and followed by the modeling component and system reliability, followed by linear regression. So as I mentioned last week, regarding the part of the queuing theory, and look at how you can use Markov chain model to analyze certain discrete or continuous probabilistic models, which is actually happen to be part of what we are going to cover this week as well. Previously we started developing models using proportionality and determine the constant of the proportionality, and we also studied a little bit on linear regression. So you already know how to analyze, build a model on how to model these problems with constant difference or with proportionality. And then this chapter, what we do is we will allow the constant of proportionality to vary in a random fashion rather than to be fixed. So earlier there was an example regarding the rental car, and then the idea was, suppose that we have someone was getting a car from Tampa, Florida, and then he decided to go to return the car in Orlando, Florida. And then if we define the first location as state 1 and the second location as state 2, we call it state being that at a certain time period of time, there are multiple states that the system can stay in. So in that case, we could say that if we model the problem as if a certain percentage of the renter would car rentals would return the car to the same location, for example, to the same state as 1, then there's a probability of P to return to 1. And then meanwhile, it has another probability to return to state 2, which would be 1 minus P. Right? So in that case, we know that for this car that started at location 1, it would go to either stay at 1, later will be returned to 1, or there's a possibility of going to 2. And then meanwhile, P for the second location, it could return to the second location with the probability of Q, and it potentially can go back to P as well, which is 1 minus go to the state 1. That's why it's called the probability of 1 minus Q. And then if you are trying to solve this problem, if you know that Q plus N plus 1 is a certain probability for PQ or Pn and Qn, and then essentially we could solve for long-term probability that 57% of the cars will be Tampa and 43% will be Orlando. So that's so that we, as you can see here, we need to define states. So essentially, if you think about, if you have already visited the example for MM1Q for a certain checkout counter, the state can be defined 0 person in the line, 1 person in the line, 2 person in the line, 3 person in the line, etc., etc. And then there is certain transition probability from 0 to 1, and from 1 to 2, and 1 stay itself, etc. So it's very much the same as this example, except that the way that we call it MM1, meaning that there is 1 counter, and then inter-arrival time of the customers is M, which is inter-arrival follows a Poisson arrival process. and then the service time is exponentially distributed service time for the checkout counter. That's why it's called M and N. So very similar in nature. And then if you look at a different example here of the voting tendencies, if we say that we can model this problem as a Republican would vote themselves with 0.7% probability, and Republican potentially could vote 0.2% probability to vote independent, etc. As you can see here, all the ones that go out from Republican should add up to 1. So in this case, 0.75. I'm trying to get a laser pointer. Hold on. You can see here, 0.75 plus 0.05, 0.8 plus 0.2. That's equal to 1. So you can see that this essentially can be defined as a matrix, and every row, the matrix, all the states would be all these different discrete states, and then each row should add up to 1. If we use state 1 being Republican, then state going to itself would be 0.75, going to the second state, Democrat, would be 0.05, and going to the third state, Independent, would be 0.2. And then if you add them up, it should be 1 for that particular row, for that's starting from Republican. So, and then this problem can be similarly can be based on the previous state. For example, for the one that's going to Republican is either coming from Republican previous state, which has a 0.75 probability, and then meanwhile it could be coming from a Democrat, and it is 0.2, a 0.2 probability, right? So you plus that portion plus the one that's coming from Independent, which is 0.4, and then that would be your new number of votings for the Republican, right? So as time goes on, you can try to solve this problem. This is a long-term probability that you would long-term probability curve that you would be able to get. So that's that, which is pretty much the same, except that now we have 3 states instead of 2. That's pretty much that actually I want to cover as how you can model a discrete system, and then apparently MM1 and etc. a Markov chain type of models are not covered in the textbook. That's why I have some videos in weekly material. You should go ahead and take a look, read through some of those, and you would understand a little bit better. I'm sure you probably have already done that because that was last week material. If you haven't done that yet, definitely spare some time to review the videos there. And then continue with the probabilistic modeling. Here we're trying to model component and system reliability, and the reliability is defined as 1 minus the probability distribution function of the failure, right? So if Ft is the failure rate of the item, and then Ft is the probability distribution, so that you can get a reliability for the. And then we know for series system, this is like in high school we're trying to study the electricity circuits. If for series systems, the reliability is really the reliability of the multiplication of the reliability of the individual components of the system. And then for the parallel system, with 2 subcomponents, the system reliability equals to the reliability of the first component plus the reliability of the second component minus the first component reliability times the second reliability there. And then if it has a series and a parallel, it will be the reliability of the series 1 times the reliability of the series 2. It happens that series 1 can be a series system, and the second subcomponent could be parallel system as well. That's how you calculate the system reliability. And then is actually, this section actually we will discuss in the linear regression here. So for a linear regression, we know it can be defined as yi equal to axi plus b, and then you would be able to solve the linear regression problem with objective function objective function, and trying to solve for the a and b by taking the first order derivative and second order derivatives and setting them to 0. You would get these normal equations, and then based on the normal equation, you would be able to solve your a and b correspondingly based on your observation of xi and yi. And then m is really the number of data points here in this case. And then some certain important aspects that we need to discuss is some square of error, which is the yi, the actual observation minus the predicted value from your equation, and square them and add them up. And then total corrected sum of squares is actual value minus average of all the observations, and then sum them up. And then regression sum of squares is total sum square minus sum square of error. And the coefficient of determination R squared is 1 minus SSE divided by SST. And then so for the residuals, when you look at the residuals of your linear regression, you want to look at whether it actually follows certain shape. For example, it could be fanning shape, could be linear shape, could be curvilinear. If that really happens, we would say that, for example, for this one, for the first one, fanning shape, meaning that as x goes up, as x becomes bigger and bigger, your error becomes bigger and bigger as well. So somewhat, meaning that your error distribution is not random, and which actually violates the linear regression assumption. In that case, you know the model could be potentially misspecified, right? And then another possibility with the residual is going up. As x keep going up, the residuals keep going up as well. This type of error distribution is something that we're trying to avoid. So meaning that something might be wrong with your linear regression if you actually saw the error is having this type of shape. So it should have been random. So if you look at the solution of the homework, look at some of you guys already done that, and then you will see that what we're really after is the randomness of the error distribution. And then homework are these, you already done that. So that's pretty much that we were trying to cover for last week. And then let me open this week's material, which would be linear programming. And then if we have time, we could potentially cover a little bit more for next week as well, so that we kind of ahead of the curve instead of behind the curve in every section, in every actual session that we have. So that's pretty much what we are going to cover, and then continue with week 6. And then we want to discuss what is optimization and what is linear programming, how to solve linear program. It has multiple methodology. One is geometric solution, the other second one is algebraic solution, and the third one is simplex method. Apparently, simplex method is a more advanced approach, or meaning that it helps you to to find ways to solve the problem more efficiently. And based on those solution methodology, we can analyze some sensitivity of the model if X changes, what's the effect of the optimal solution, etc. And then we can briefly discuss numerical search methods in this section as well. So in the chapter, previously in chapter 3, we said that 3 criteria for fitting or selecting a model collection of data. You want to minimize the sum of the absolute deviation, minimize the largest of the absolute deviations, Chebyshev criterion, or you minimize the sum of the squared deviation, least squares criterion. So I want to comment that in chapter 3, homework, we have a homework that's actually trying to minimize this largest of the absolute deviations. In our session, I tried to explain that problem. Apparently, I think not a lot of you actually got it. And either 1 or 2 of you actually did it correctly, meaning that either you didn't get the idea, or it's just you just don't on the right track. So I'm sure you definitely should revisit that problem, look at the solution for this particular problem, and then you would understand better. Maybe let me pull up the solution and give you a sense on what I'm trying to say here. No, it's week 3. Yeah, the example was really trying to minimize largest deviation between those 2 data sets. And then if you use certain methodology that we actually discussed this part in the class, and then if you make certain substitution, and then you're trying to set up your problem, it's really a minimization problem, minimize .r with certain constraints. That part of, I don't think any of you actually get it correctly. At least not everybody. I think majority of you didn't get it correctly. So take a look at this answer and understand it. And then it happened that formulation was there, but the solution, how to solve this problem, is going to be covered in this chapter. So let's continue there. Hold on. Let me pull up the slides again. Okay. So, and then what is a linear program? Linear program is the objective function and the constraints are all linear. So meaning that there's no nonlinear functions in the model. And then that's a linear program. And then when we actually continue with some other things, we say that basic model is just trying to optimize certain function, and then function is a function for x. In x could be a vector, and then for all the j's, which j belongs to a bigger j there, that's our basic model, and then that function is called objective function. That's going to be our objective. So this function is the objective function. And then we can define all the x's or the vectors as the vector of x as the decision variables. And then with that being said, you have to try to satisfy certain constraints, meaning that certain x's mixed up cannot exceed certain value, or certain x's mixed up cannot be less than or equal to a certain value. That's called constraints. And then that certain value that I just mentioned is considered to be as right-hand side. And then it has been used in many places, including airlines trying to solve optimization problem to best utilize whatever resources available and trying to minimize the running cost. And then in online delivery, online e-business such as Amazon, they do very similar optimization as well to see what's the best way to distribute, to send the products from certain distribution center. For example, if you order something from Amazon, it could be from the product that is being sent could be from a nearer location that's nearer to you. That's really some sort of optimization problem that they're trying to solve. In addition to that, some other like inventory problem, it's also an optimization problem in some regards. We have the homework on the inventory aspect as well, even though for the optimization type of problem that e-commerce business are facing is a little bit different from the homework that the way that we're trying to approach for the homework problem that we went through. So that's the 3000 view of the optimization problem. So let's see, and then optimization problem can be classified as unconstrained or constrained, meaning if you don't have any constraints here, you only have objective function, then that's called unconstrained optimization. If you have objective function as well as constraints, then it's called constrained optimization problem. And then let's take a look at what is a linear program. And then linear program is, number one, has a unique objective function. Decision variable has a power of 1. So if you have a x1 and x2, you don't want to have a function form of x1 times x2. If that happens, then the decision variable doesn't have a power of 1 because the function itself becomes quadratic if you use x1 times x2 as in your objective function. And with that being said, which is the third bullet here says, no product of decision variables in the objective or the constraints and the coefficients of the decision variables in the objective function and each constraint are constant. So essentially saying that 3x1 plus 5x2 equals something or larger than equal to something. And then the decision variables are permitted to assume fractional as well as integer values. So in this case, we call it as a linear program. And then later, next chapter, or the chapter after, we discuss integer program, which is essentially using, instead of, the only relaxed there is the last condition, saying that the decision variables can only be integer instead of fractional. So if it can be fractional as well as integer, then it's called linear program. Otherwise, it has to be called integer program. And then sometimes we call it mixed integer program, MIP, only because the decision variable can only be binary or integer. So in other words, it can only be 0 or 1 or integers, then the problem becomes MIP, mixed integer program, instead of a linear. So there are all other types of optimization problems, including multi-objective or Go programs, nonlinear program, dynamic program, stochastic program, and MIP I already mentioned. But this course actually we only cover linear program, nonlinear program, a little bit on the nonlinear program, and also the integer program as well. We don't cover the rest of the other classes of the optimization. Hopefully, if you really need some of those knowledge, you will be able to do some research after this class, so that you get a gist of what the model, all these type of the optimization algorithm are trying to do. So suppose that we use this as an example. If for the space shuttle cargo, I couldn't remember. It's yeah, I kind of remember now. So that says that. So suppose that you can only cover. This is also, this problem is also called um, knapsack problem. So meaning that if you go out to a camping trip, and then you have certain constraints on your what you can carry in your bag. So there's a volume constraint. Suppose in this space shuttle cargo example, this big V is really the volume constraint, because if you take on Yj, you take certain space, which is smaller case of Vj, right? If you decide here, you can decide on which one you're trying to take. You can either take Yj equal to 1 if item j is taken, otherwise it's 0. So if you take Yj, the volume that the space that it needs is Vj. So use Vj times Yj is the space that you actually have to have for a specific item j. If you sum all of the items together, you have to, all the spaces used has to be less than or equal to the volume constraints in this case, right? If meanwhile we have a weight constraint, we say that, oh, I cannot really carry more than 20 pounds of stuff in my backpack, then you have a weight constraint. Same thing, you just use Wj times Yj, sum them up, has to be less than equal to W. With that being said, these are all the constraints. Then what we're trying to maximize? We're trying to maximize really is the benefit that I can get if I carry Yj. If I carry Yj, I get Cj amount of benefit, and then if I don't carry Yj, then I don't have anything. I don't get any benefit from that particular j item, right? So that would be the maximize Cj, Yj, sum them up. That's the objective function. This is the one integer optimization program, because you are trying to make a decision on what you are going to tick or not tick. It's a decision of a binary variable. It's a linear integer program in this case. Any questions on it? No? That's good. Okay, let's continue. And then here we divert a little bit. We see that how we can approximation a piecewise linear function. So you can see that if we are trying to if we can try to solve certain problem here, or we can try to minimize the slope for piecewise linear, trying to minimize this function subject to x1 is less than or equal to 0, larger than or equal to 0, but less than or equal to y1 times a1. And then this is one way that we can use linear linear programming to try to figure out the coefficients of the linear approximation, piecewise linear function that we talked about here. And then let's just go a little bit deeper on a specific example on the linear programming. So suppose that what we are trying to say is for a carpenter, if he has limited supply of lumber, so that he is thinking about how many desks or how many chairs he should be producing using the limited supply of the lumber that he actually has. And then he also have a limit on his labor that he is trying to put into the producing the chairs and tables. Suppose that one table actually you can sell it for $30. So let's assume that X2 is really the number of tables that you can sell. you can sell, you can produce. In some regard, in this case, you can say that the carpenter can produce X2 units of tables, and then as a result, if we sell those X2, he can get $30 for each of the units, so that he can get 30X2 amount of money if we produce X2 units of tables. But meanwhile, for the chairs, if he produces one expensive chair, which actually costs $25, then, or let's say that X1 is one set of chairs, 4 chairs, then you can sell it for $25. Then 1 unit of the chairs, this unit will be four of them, and then you can sell for $25. Then in that case, we can try to maximize 25 times X1 plus 30 times X2, with constraint that because each unit of the X1 number of chairs, you would take 20 square foot of the lumber, for example, and then but the table itself probably takes 30. Then in that case, you have to use 20 times X1 plus 30 X2, less than or equal to 690. That's your lumber resource constraint. And then on the other end, if there's a labor constraint that you can only spend 120 hours on building all the on producing the chairs and tables, then we can set up the second constraint. And then meanwhile, X1 and X2 has to be larger than or equal to 0. We know that we can only produce certain units of the tables or chairs. But in this case, apparently we are allowing the X1 and X2 to be fractional number only because we're using still using linear programming as an example to talk about linear programming here. So we don't have the constraint of X1 and X2 have to be integers. So now, if we look at this problem at the bottom, and then next question is, how can we represent this problem in the two-dimensional space? So in the two-dimensional space, what we really have is, let's look at the graph on the right-hand side. And then we actually know that if a line on a two-dimensional space is really 5x1 plus x2 equal to 120 is really this constraint, right? Because when x1 is 0, we know x2 should be 120 divided by 4 should be 30, which is that 0, 30 that defines this one of the points that should pass through for this line. And then the second point that it should pass through is when x2 is 0, x1 should be 120 divided by 5, which is 24. So that's another point that it should pass by. So this whole line is really that function, which is 5x1 plus 4x2 equals to 120. And then if we have a constraint that says less than or equal to 120, essentially we're saying that it can only go to this direction of that line, right? And then for the other constraint, which is 25 plus 30x2, 25x1 plus 30x2 equal to 750, is really defined by this line. You can, its second constraint is really, which is constraint 1 I'm talking here in this graph, in this formulation, it really should be 20x1 plus 30x2 less than or equal to 690. And then you will find out that this line is the equality of this function, which is 20x1 plus 30x2 equals to 690. And then if we have to satisfy this relationship, it has to be anything in this area that's beyond on this side of the curve, right? And then meanwhile, we have this x1 larger than or equal to 0, so it has to be on this direction, and y has to be in that direction. All of them, if we put all the intersection of all those 4 constraints together, we see this shape, which is the shaded area. We call this area being feasible region. That's important for the linear program. This area is called feasible region. In other words, if you look at this first chart, it essentially says anything that's not shaded is called infeasible. It's the infeasible region because it would not satisfy one or more of the constraints, right? So in other words, this point that I'm highlighting here would satisfy constraint 2, but it doesn't satisfy constraint 1 just because it's not on this side of the constraint 1 curve. And then this point really satisfies constraint 1, but doesn't satisfy constraint 2. And then with that being said, once we set up the feasible region, next question is, what's the objective function? The objective function is 20x1 plus 30x2, and then we would be able to know this is really, if we set this up equal to y is a constant, and then you would know that those lines would be parallel to the dotted line. It would be parallel to the dotted line. If we are trying to maximize that value, meanwhile, you have to satisfy all the constraints. Apparently, it has to be this point. Then we find the solution that can maximize its objective function and satisfies all the constraints, right? So that's one way to look at the linear program problem. It's geometric way to look at the problem. And then if we see that apparently the solution really depends on the slope of the objective function. If we say that we're trying to maximize 30x2, 30x2 is what? Let's use 25x1. If 25x1 is really a function more look like that, right? 25x1. So it would be, if we use parallel trying to maximize that, then the line should go here, 25x1. And then this would be your maximum solution. 25x1, hold on. 25x1 is actually this way. So that you're trying to find this solution, which means the x1 has to be 24, so that it would be able to get that 25x1. That's that I'm trying to cover here. So that's the step 1 of the linear programming. And then it's same thing as what I just discussed. We're trying to find out a feasible region. Meanwhile, the objective function is increasing in that direction, and the objective function is decreasing in that direction. If it happens that that's our objective function, and then it's the level curves, the parallel curves that are trying to minimize or maximize. So it really depends on the objective function. If it's maximized, then that's the solution. If it's a minimization, then that's the solution that I'm pointing out to there. So that's the geometric solution approach for linear program. And then the second way we discuss is called algebraic solutions. The way that you do is you find all the intersection points of the constraints. In this case, that we just take a look. In this case, all the intersection points would be 1, 2, 3, 4, as well as those two, because x1 larger than or equal to 0 is also one of the constraints, right? So that's the way that all the 6 points that we have, the intersection, and then we evaluate all of them, determine which intersection points, if any, are feasible to obtain the extreme points, and then evaluate the objective function at each extreme point. And the intersection points, we're saying that if any feasible to obtain the, determine which intersection points, if any, are feasible to obtain the extreme points. In this case, even though I said the first step would be looking at 1, 2, 3, 4, 5, 6, all of those 6 points, But if you look at the feasibility, those two are not feasible just because of the reason that I presented earlier. It's not even in a feasible region. So you don't really evaluate those 2 points. You only evaluate the rest of the 4, those 4 intersection points, and then pick the largest value that you can get for your objective function, and then you find your optimal solution. That's what here is trying to see, and then choose the extreme points with the largest or smallest value of the objective function, and then the computation complexity is apparently intersection point enumeration. So if we have more constraints, it becomes more complicated in the way that we can define. And then you actually have a theorem, even though here in the textbook it didn't mention too much there, but the theorem is really trying to say is for any linear program, the optimal solution always happens to be at the extreme points, at the intersections. So that's why by doing this, it guaranteed that you can get the optimal solution. But why is that the case? It's really beyond the scope of this course. If you are interested in, you should look into why a linear program always have optimal solution at the extreme points. And then the third step that we're talking here is a simplex method. Here I have to really to let you know that is I'm actually not going through the whole real detail of this, but I want to say that when you do the homework for the simplex method for this week, definitely do it by hand. I'm not expecting that you should do it using a computer using R, because I want you to understand the relationship of what is the simplex method, and then you would be able to solve it. But the basic idea is a Gaussian elimination, meaning that you're trying to eliminate some of the x's or some of the different x's or your supplementary variables, and then at the end it satisfies the optimality test, and then you will be able to find the optimal solution. And then it says equivalent system equations by eliminating the new dependent variable from the equations, and then just keep going. Usually after 2 or 3 steps, you would be able to find the optimal solution. And on how to solve this, apparently, let me see if we have time. If we do, I would rather to try to cover that. Probably, yeah. Let's do this. Let's continue with the lecture, and then if we have time, we go back to 2073 and 75 to look at how we can actually solve a linear program using simplex method. And then beyond that, two types of sensitivity analysis. One type is what is the effect of changing the value of the profit for each table. So one of the decision variables. That's one way to look at the sensitivity. And then the other sensitivity that we actually look at is what is the change of the objective function if one extra resource is available. Suppose that you have one extra square footage of lumber, what your objective function would change after you find the optimal solution. And then that one of the economic interpretation of this type of sensitivity analysis is called marginal value. And then there's another type of analysis is related to the shadow prices, which is the first type of the sensitivity analysis. In other words, what we're doing in certain macroeconomic analysis is macroeconomic theory. It really depends on the optimization theory. Okay, and for numeric research search methods, we have unimodal functions. Potentially, we could find local minima or global optimum solutions. These type of solutions are something that we're trying to briefly discuss in the textbook. And then one of the approach is called dichotomous search algorithm. Is you have, if you already know the value of A or B, you're trying to find the midpoint, and then you're trying to narrow down the search area, which is called dichotomous search algorithm. It's actually also called bisection or something like in that nature. But the idea is actually very simple. Just evaluate 2 points, and then it's not in the value is that what you're trying to look for is in between, and then you just cut the other half and try to see where it actually lands in. After multiple iterations, you would be able to find the solution. And then, of course, golden section search method very similar to the dichotomous search algorithm, except that it uses that golden search rule, which is first section is following this form, and second section is following that function form. These are the homework, and again, for the linear program, definitely you solve it by hand using simplex method. So let me quickly go through the simplex method there from the textbook. Before we do that, let me see what we have for next week. Yes, maybe it's worthwhile for me to continue with the next week material because we started a little bit late here. So let's make that makes sense. Probably hard for us to. No, it's probably hard for us to finish that part. So let's continue with the briefly go through the linear programming approach. Bear with me and let me open the textbook. Meanwhile, if you have any questions, feel free to ask. Here is a summary. So let's continue with this example of the carpenter's problem. So the step one is really trying to put the function to a tabular format. And then the way that we see is because you have to, because it was non-equality, right? So you see that remember that the first constraint was 20x1 plus 30x2 less than equal to 690. So you have to add something so that it's equality. So you add that something which is called y1. This y1 has a special form. It's called, it's not on top of my head. y1 is called, y1 is, it's a supplementary decision variable. So it's called, we find the value of the dependent variable x1 at, let's say y1 is called what? Go back to the home page. Okay, it's called slack variable. That's correct. So if you say that slack variable itself can be a negative value. So in this case, because it's always less than that value, so if you have a slack variable, it would be a positive value, right? And then here I actually have more discussion here says if a negative value for yi indicates the constraint is not satisfied because we use variable yeah because we actually define that slack variable has to be non-negative. So so with that being said, we also define slack variable for the objective function, which we use as the z. But you have to realize that the objective function is we know x1 is larger than or equal to 0 and x2 is larger than or equal to 0, so that supposedly it would be this function form, 20x1 plus 30x2 larger than or equal to 0. And then in order to use non-negative slack variable, we have to times -1 on both ends, so that you come up with objective function as a constraint in this format that we just saw, the third equation. And then with that being said, if we add y1, y2, and z into the equation, you just would be able to come up with the tabular format. That is the tabular format that we are after. And then if you go a little bit further in the textbook, you would be able to see that it's really initial table is this is probably not the initial table, but you would see this one is the initial table. And then once you get this initial tableau, next step is trying to find. Step 2 is saying that you find the initial extreme point, and then what you're trying to do is just trying to using this tableau to look at the optimality and all type of tests and design on which is the enter variable, which is the exiting variable, and doing pivot so that you can get a new solution. And then at the end, there is a way to check the optimality test, and then which is based on this value with the objective this objective of the objective function. Oh, the optimality test, because x1 and x2 has to be positive, but here it's negative, so it doesn't pass. And then you just keep going until all the way to, at one step, you would see that satisfied the optimality, and then you would see this is really your objective function, and then the objective value is 750 in this particular example. If we go through this example, it's actually rather straightforward. There is also a different example here as well. So I just want to point out that you have to add a non-negative slack variable in order to get to equality constraints. And then this slack variable later on, you actually, this limited discussion here, it is the shadow crisis that we actually discussed. Okay, that's pretty much that I want to cover today for this section. I don't think we have time to capture next section, which is actually a little bit intensive as well. So next week, you would have to learn a little bit about the decision theory yourself. And then after that, we will continue with a different section. So I'll see you 2 weeks from now in terms of the lecturing. And next week, I will host office hour as well at the same time, 8 o'clock. Last week, because of the password change, I wasn't able to log in. I actually got the new password even until this morning. Someone in the IT department changed the password without informing any of us, so that's actually unfortunate. But if you have any questions, send me an email, and then we can also schedule something up if you need to talk about anything. Okay, any other questions for today? No? So if you don't have any other questions, we can just stop here. If you do, send me emails, etc., and then we can discuss. Oh, just a reminder, I want to say, I also sent an email out. A lot of you guys actually didn't participate into the discussion forum. I think you should definitely do that. It's 3 points for you. So it also counts for, I believe it was 14% or something, or maybe 20%. So why not? Go ahead. Definitely do that with the discussion. And if you have any questions, ask me or either in the Blackboard system or send me an email. Okay, that's it. If you don't have questions, we can stop here. Good night, everybody.